As an application of our equilibrium expressions for the bending of beam, let's look at a simply supported beam with a point force in the middle. So the force will have magnitude P acting on it, and it's located right in the center of the beam, and it's a simply supported beam, and that means that it's pinned on the left side and it's sitting on a pin roller on the right side here. And let's go ahead and find the internal force diagrams for the beam. So I want to go ahead and find V as a function of x, so the internal shear force, the internal moment, M, as a function of x, and the internal axial force, R, as a function of x. And we'll go ahead and do this two ways. One, we'll do it using sort of free body diagrams and section cuts, so a step-by-step. Another one is we'll go ahead and look at using our differential equations of equilibrium to get the same results. So first, let me go ahead and make a free body diagram of the beam and draw in the support reactions. So on the right side there's a vertical force, I'll call that R1, and on the left side there are reaction forces R2 and R3 as I've indicated here, and then there's the force P acting in the middle of the beam. So first, just some of the forces in the x direction is going to tell me that the reaction force R3 is going to be equal to 0. So my coordinate frame here is the usual one, so x along the length of the beam and y in the vertical direction and z coming out of the plane at you. So R3 is going to equal 0 in this case. And so if I make a section cut someplace along the length of the beam, I'm going to end up with a vertical shear V and a moment M and an axial force R, internal force, and that internal force is always going to have to be equal to 0 in this beam. Okay, so that gives me R of x is just constant value, and the constant value is equal to 0. Now, if I go back to my original free body diagram of the whole beam, so I have the force P acting downwards, and then I have the two support reactions of vertical directions R2 and R1. Sum of the forces in the vertical direction says that R1 plus R2 is equal to P. And if I take moments about the left end here, which I've labeled A, I find that R1 times L is equal to P times L over 2. And that allows me to solve for the right side reaction force. R1 is equal to P over 2. And if I plug back into the vertical equilibrium equation, that then tells me that R2 is equal to P over 2. So the force P is supported equally on both sides of value P over 2 in this beam. So let's go ahead and draw a free body diagram again of the left side here. We'll make a section cut in an arbitrary location x from the left end of the beam. So we have the vertical force P2 acting on the left end, and then we have our shear, which I've drawn in the positive sense, so V of x, and we have our moment about the z-axis M of x. So we can now do equilibrium on this piece. If I sum the forces in the vertical direction, I find out that V of x is equal to minus P over 2 to keep vertical equilibrium. And if I take moments about the location x, so that's the distance from the left side that I made my section cut, then I find out that M of x has to equal P times x divided by 2. So that gives me the moment, internal moment at this section cut here. Now, the section cut that I've drawn here is one that is to the left of the force P, because there's no vertical force shown in my free body diagram here at the center of the beam. If I make the section cut to the right of the applied load, now my free body diagram looks a little bit different here, because I have to include this vertical force P acting in the downward direction. So, but again, I've drawn in my internal force V and my internal moment M, and I can again write the equilibrium equations in the vertical direction, so some of the forces in the y direction and some of the moments about the z-axis. And if I write those two equations down, I find out that the shear force V is now plus P over 2, before it was minus V over 2. And if I sum the moments again at the location x, I find out that the moment is PL over 2 minus PX over 2. So I have to include now this force here and the moment that it creates through the lever arm to the section cut location. So I can draw the internal force diagram. So V of x starts out at minus P over 2, and then it jumps up to a value of P over 2 in the second half of the beam. The moment itself, if I plot it, it's a straight line linear going up from 0 up to a maximum value at L over 2, and then from L over 2 downwards to L, it goes back to 0 linearly again. So these are the shear and the moment diagrams as functions of x for the beam here. Note that there is no distributed load in the section to the left of the force P or to the right of the force P. And so in those sections, I find out that dv dx has to equal 0, which means v is a constant. So I get one constant to the left of the load and a constant to the right of the load, and it happens to be a different constant, but it is a constant in those two sections there where the distributed load is equal to 0. The shear in each one of these sections is constant, and so that tells me that the moment has to be linear, and that's because dm dx plus v equals 0. So I have a straight line rate of change for m of x in the first section, and I have another linear function m of x in the second section. And the constant, or the slope of these lines, changes. It depends on which section of the beam I'm in. So in the first section of the beam, I have a slope of minus p over 2. In the second section, I have a slope of p over 2. Now, the other way we could solve this problem is by looking at the differential equation, and to use the differential equations, I have to know what the distributed load is. But I just have a point force in this case. So just like before, point forces are represented by delta functions, and the delta function is located at L over 2, and the force is pointing in the downward direction, so in the minus y direction, so I need a minus sign. So minus p delta of x minus L over 2. I can put that into the force equilibrium equation in the y direction, so I move it to the other side, I'll get a plus sign, and now I can integrate this equation. I'll integrate from 0 to x, and so I get v of x, so the shear force at any location is equal to the shear force at x equals 0 plus p times the Heaviside step function located at L over 2. And the shear force at v of 0 I can get from the free body diagram of the end of the beam, which shows me that there's a vertical shear force p over 2 on a face pointing in the minus x direction. So that tells me then that v at 0 is equal to minus p over 2. So remember, the sign convention that we have for positive forces is that shear forces on leftward facing section cuts have to go downwards for the positive value. So, and I have one going in the vertical direction or upwards, so I'm going to end up with a minus sign here. So my final expression for v of x is minus p over 2 plus p times the step function at L over 2. So it starts out at a constant value of minus p over 2, and then it jumps by a value of p when I pass the load at the midpoint of the beam. So you can just redraw that or plot that function. Now, the moment relationship is dm dx plus v equals 0. So I can plug in for v and move v to the other side of the equality. So I'll get p over 2 minus p times the step function, and now I'm going to integrate again from 0 all the way to some arbitrary location x. So I'll get the moment at x is equal to the moment at 0 plus px over 2, so that's the integral of this first term here. And when I integrate the step function, I end up with the Macaulay bracket here. So we get minus p, the Macaulay bracket of x minus L over 2 in this system here. So, and m, or the moment at x equals 0 is 0 because there's a pin, it's free to rotate, so there's no moments. And if I go ahead and plot that function, I end up with the exact same graph that I had before. I have a linear rate of change, and then when I pass the midpoint of the beam, it's going to flip sign on the slope, and I end up with a linear rate of change, and I have 0 moment at x equals 0 and 0 moment at x equals L, which I need to have because I have pins in the system.